My dear friends, in the previous classes we have discussed a lot of things about the electric field, then electric field lines, and in the third class we have discussed a lot of things about the electric dipole at axial and also at equatorial. Today we are going to discuss about the class 4 of the electric field, that is electric dipole in an electric field. It means previously we have discussed that an electric dipole consists of a charge plus q and minus q. Hence, when an electric field dipole is placed in a external electric field, what happens? Today we are going to discuss about it. An electric dipole placed in an external electric field. Let us consider an electric dipole AB is placed in a uniform electric field of strength E vector. As we know that a dipole consists of two charges plus q and minus q. So plus q charge experience a force along the direction of electric field, while minus q charge will act a force opposite to the direction of electric field. Hence there is two equal and opposite forces are acting. But listen to me. In this case, what happens? The net force, here force is plus QE and here force is minus QE. So the net force is zero. So when the dipole, in this case the force and this force are equal and opposite but having different line of action. So they constitute a couple or a torque. It means when an electric dipole is placed in an external electric field, what happens? It will oscillate or it will move here and there. Let AB is an electric dipole consists of charges plus q and minus q respectively. Therefore, electric dipole length AB is equal to 12. The distance between the A and B, the two charge is 12. Implies electric dipole moment. Last class we have discussed the dipole moment is equal to the magnitude of either one charge and the distance of separation of the dipole length. Dipole length is equal to magnitude of one charge, that is q into 2L. 2QL. Let the dipole is placed in an external electric field E vector inclined at an angle theta. It means the dipole and the electric field are acting at an angle how much? Theta. Clear? Therefore, force on each charge plus or minus QE. Force or net force on the dipole is equal to 0 because this plus QE and this minus QE are equal and opposite, hence they cancel each other. Clear? Okay? Get it? Therefore, as these forces are equal and opposite, having different lines of action, so they constitute an electric, so they constitute a couple or torque. Listen to me, this force is active, this force is this. They may be equal and opposite, but they are having different line of action, so they constitute a torque or a couple. Therefore, torque is equal to linear force on either charge into perpendicular distance. Listen to me, let this length is x. If you find the sine theta, then sine theta is how much? Height by hypotenuse, that is x by 2l. Therefore, perpendicular distance is 2l sine theta. So, linear force is either one force on the each charge. The force on the each charge is how much? QE. The perpendicular distance is 2l sine theta. It means here Q is there and here 2l. Okay, charge into length. So whenever we are going to discuss about the charge into length, that is for how much? That electric dipole moment P. So I can put it as a PE sine theta. How much? This is torque, or I can write it as a tau is equal to, in vector form, tau is equal to P cross E vector. Clear? Tau is equal to P cross E vector. Clear? So here torque is axial vector, or we can take it as a pseudo vector. If the dipole moment is acting in such direction, electric field is taking that direction, and then tau vector will be perpendicular to PE, will be lying in the plane, then torque will be acting how much? Along the axial vector. Clear? So torque is a vector quantity, as we know it from the previously from the first year classes, rotational motion. Clear? So I would like to say that what happens when a dipole is placed in a uniform electric field? It will deflect. Answer: it will deflect. Now, this is a very, very important question. Comes as a 2-mark questions in general. Different cases. Case 1. If dipole is parallel to electric field, it means this is a dipole, this is parallel to electric field, is moving along the direction of electric field. Then theta is equal to 0 degree, sin theta is 0, so torque is equal to P sin theta is equal to 0. Clear? Case 2. If P vector opposite to E vector, so theta is equal to E. It means dipole electric field is moving that direction. Means dipole is moving at that direction, opposite. Cos theta is, sorry, we need sin theta here. Sin theta again 0. So torque is 0. Case 3. If a dipole moment is perpendicular to electric field, theta is equal to pi by 2, sin theta is equal to 1. Therefore, tau is equal to P maximum. I hope this is the question in 2019. At which angle the dipole should be placed in an electric field so that it produces a maximum torque. So to be maximum torque, the dipole moment must be perpendicular to the electric field. So that theta is equal to pi by 2 and sin theta will be 1 according to the formula. Tau is equal to p sin theta and sin theta becomes 1. Hence tau is equal to p. This is the in general questions. Now there is another question which regularly comes. This is a uniform electric field while this is non-uniform electric field. 2018. What happens when an electric dipole is placed in a non-uniform electric field? Listen to me. Here, these lines are parallel and equidistant, so it is represent a uniform electric field. Well, these lines are not parallel, so it is represent a non-uniform electric field. It means I would like to say that electric field at this point is not equal to at this point. So I would like to say that if a dipole is placed in it, in such region, so let it will be B and minus Q charge and let it will be A plus Q charge. Clear? So here electric field is something else. So this force, this is F1 and this is F2. F1 force not equal to F2 force. They are not equal because electric field is not equal. That's why net force, there is summation of force not equal to 0. But in this case, force F is equal to QE. So here electric field and here electric field both are same. Charge is, magnitude of charge is same. So force is 0. But in this case, force are not equal. So here when the dipole is placed in a uniform electric field, it only deflect. It means only rotational motion. Net force 0. While if the dipole is placed in a non-uniform electric field, force not equal to 0, torque not equal to 0. It means then linear force F not equal to 0, rotational torque not equal to 0. That is it explains both linear as well as rotational motion. It means when the dipole is placed in non-uniform, it deflects as well as it moves ahead. It means there is also some linear force as well as some rotational force. So when the dipole is placed in a non-uniform electric field, force not equal to 0, torque not equal to 0. But here, in this case, force is equal to 0 and torque is equal to torque not equal to 0. That is P is sin theta. Clear? This is about an electric dipole when placed in an external electric field. But listen to me, when the dipole deflects, there is a change in its angular displacement. It means when the dipole rotates or deflects, there is a change in angular displacement. Hence, there is some work is done, and that is called work done by an electric dipole when placed in an external electric field, and that is called potential energy of an electric dipole. Potential energy of an electric dipole when placed in an electric field. Let AB is an electric dipole consist of charges plus Q and minus Q is placed in an electric field at an inclined at an angle theta. E the dipole length AB is equal to 12, hence electric dipole P is equal to Q into 12, 2QL. Let the dipole is placed in an external electric field E vector inclined at an angle theta. Therefore, torque acting on the electric dipole tau is equal to P sin theta. Okay, whatever we have proved just few seconds earlier. If d theta is the angular displacement by the torque and d will be the work done, okay, then dw is equal to tau into d theta. Pe sin theta d theta, because we know that torque is equal to P sin theta, just now we have proved. Integrating both sides with proper limit, dw. If there is no work done, initially the work done is 0, and after final work done, the total work done will be W. Okay? P E sin theta d theta. Clear? From if there is no work done, initial angle is theta E. After work done, the final angle is theta F. Therefore, W is equal to 0 to W. P E sin theta d theta. Sin theta d theta integration how much? Cos theta theta I theta F. Clear? So W is equal to PE initial angle minus cos theta F minus cos theta I. Okay? If you solve it, W is equal to PE cos theta I minus cos theta F. Clear? If theta I is equal to pi by 2, it means initially the dipole is perpendicular to the, if the dipole is initially perpendicular to the electric field, then theta is equal to pi by 2, cos theta I is equal to cos pi by 2, 0, and theta F will be theta, that is the final angle. Then W is equal to PE cos theta is cos pi by 2, 0, 0 minus cos theta, or W is equal to minus PE cos theta or W is equal to minus P dot E vector. Okay, now I will discuss the three cases. Case 1. If theta is equal to, final angle will be theta f is equal to theta is equal to pi by 2. It means initial angle is pi by 2 and the final angle is also pi by 2. Then how much? Cos pi by 2 again 0. So what term is 0. Case 2. Theta f is equal to theta is equal to 0 degree. Let the dipole is initially parallel to the electric field. Okay? So if the parallel to the dipole, then theta is equal to 0 degree, and we know cos theta is equal to plus 1. So what term will be how much? Minus P cos theta. It means minus P, that is minimum. Earlier we know that from the study of metals. When a body possesses minimum potential energy, it is more stable. Clear? So at this condition, or when theta is equal to 0 degree, the dipole possesses minimum energy, that is electric dipole is more stable. This is also called stable equilibrium. Clear? Now the question arises, at which condition the electric dipole is said to be more stable? It means when the dipole is parallel to the electric field or theta is equal to 0 degree, it possesses minimum potential energy, and that is called stable equilibrium. Clear? Case 3. If theta f is equal to pi, it means opposite to it. Then we know that cos theta is equal to minus 1, or what term is equal to minus P cos theta. So cos theta is minus 1, minus plus. So answer what will be? Plus P. That is maximum, and it is called, when the body possesses maximum potential energy, it is said to be unstable. Hence the body, or here in case of electric dipole, becomes most unstable. That is unstable equilibrium. Clear? Still now we have discussed a lot of things about the electric dipole, torque due to an electric dipole, and work done due to electric dipole or potential energy stored in an electric dipole. Now we will discuss some questions related to it. An electric dipole initially parallel to the direction of electric field is rotated through an angle of 60 degree by the work done double, then find the torque at that Listen to me. An electric dipole initially parallel to the dipole. So theta I is given. Parallel means initially parallel. Parallel is given. Theta I is 0 degree to the electric field. Is rotated through an angle. So theta F is given 60 degree by the work done double. So work done is equal to PE cos theta I minus cos theta F. This is the formula. Okay. So if it is so PE cos theta I means cos 0 degree minus cos 60 degree. So PE cos 0 is 1, cos 60 is half, and then it is found to be PE by 2. Clear? Now, tau is equal to PE sin theta, PE sin 60, because at that position the angle is rotated through an angle 60 degree. So tau is equal to PE sin 60, and it is found to be PE sin 60 is how much? Root 3 by 2. So root 3 into P by 2 is equal to root 3 down. This is the answer. Clear? So if it is rotated through an angle 60 degree by the work done double, then find the torque at that point. Hence tau is equal to, or the torque is found to be root 3 double. Clear? Next question. An electric dipole of dipole moment P is placed in an electric field of strength E and rotated from unstable equilibrium position to the stable equilibrium position. Find the work done. Listen to me. What is the question given? Dipole moment P is given. Electric field E is given. Rotated from unstable equilibrium. Unstable equilibrium. Position means theta is equal to how much? Pi. To the stable equilibrium position, theta is equal to 0 degree. Then work done, W is equal to PE cos theta I minus cos theta F. So PE cos theta I initial angle is how much? Is rotated unstable. So this is our theta I position to the stable equilibrium position. So theta is our final angle. So cos pi minus cos 0 degree. So PE cos pi is how much? Minus 1 minus answer minus 2PE. How much work is done? Answer is minus 2PE. Clear? So in such way we can find out number of questions. Some bit questions are little bit typicals, and very conceptual questions we'll discuss. Cross product of electric dipole moment and electric field is this. Dot product of electric dipole moment and electric field is how much? Listen to me, here cross product is given. So P vector cross E vector is torque, we know it. So it is torque. Clear? So it is very easy question. But whenever the question is dot product of electric dipole moment, as we know that W is equal to minus P cos theta, we can write it as a P dot E vector. Clear? It means the dot product is work done or is potential energy of an electric dipole, or it is also called as work done of an electric dipole. Clear? So in this topic we shall discuss a lot of things about the electric dipole. Dipole when placed in an external electric field, if it is a uniform, then it must have only torque, no linear force. Whenever it is placed in a non-uniform electric field, it possesses both linear force as well as rotational motion. Then we will discuss a lot of things about the potential energy stored in an electric dipole. We will discuss later on or in the next class about the electric flux, Gauss law of electrostatics, etc. etc. Till that, bye. Thank you. All the best.